Okay, so 3, negative 3. I'm going to go right 3. I'm going to go down 3, and you can picture that point, right? And if we're talking in algebra, we're talking about angle in standard position. Now, I really don't know how I got to that angle, right? Like maybe that was a positive angle that's more than 270. Maybe it's a negative angle. I am going to mark it as like the negative angle just because then it will be inside my triangle when I'm done. But we want to do the 6 trig functions of theta. So we'd like to be able to say what sine, cosine, and tangent are. And then, of course, we'll go back and we'll flip them for the reciprocal. So I'll just put the 3 basic ones up there now. Okay, well, right now, you have an angle. But you don't really know how to do the trig functions unless you have an actual shape of a triangle. So what we're going to see today is we're going to be building triangles in the 4 quadrants. And there's one rule for the triangles in the 4 quadrants. When you build your triangle from like the point that you've been given, you always have to go back to the horizontal axis. So you have the horizontal axis that's x, you have the vertical axis that's y. When you want to close off your shape and make it a triangle, go back to x. Whether you're in quadrant 3, quadrant 2, quadrant 1, quadrant 4, go to that point and go back to the x-axis. I made a right angle, right? Perpendicular. Okay. So now I built this little right triangle right there. And because I know this point is 3, negative 3, what could I label this side right here? 3. And this side I can label, I could label it 3, and I know this is going to go against your geometry nature, but I'm actually going to label it negative 3. So here's like a new thing that we have never done before. Like the side of a triangle can't be negative. I agree. But remember, we didn't used to have negative angles either. So I'm saying the side of the triangle is not a length of 3. Thank you. Okay, or length of negative 3. Side of the triangle is not negative 3. Obviously, the length of that triangle is 3. But when you're working on the coordinate plane, can you have x and y's that are negative? Yeah. So if you have any triangles that you would build in quadrant 2, quadrant 3, or quadrant 4, you're going to have one or maybe both coordinates be negative, right? In quadrant 2, x is negative because you're going left. In quadrant 3, x and y are negative because you're going left and down. So in quadrant 4, y is negative. So we're going to label it as negative 3, which goes against our geometry natures, but we're going to be okay with that. Could you find the missing side of that right triangle? What would you use? The Pythagorean theorem. And we would normally call this the hypotenuse. We're going to see on the next slide that in algebra, when we look at it on a coordinate plane, not just geometry anymore, right? We've got to shift our mindset. We're not going to call it the hypotenuse. We're going to call it r. It's almost like a radius. Okay. So we're going to call it r. And you guys said use the Pythagorean theorem. So r squared equals 3 squared plus negative 3 squared. Won't that be r squared plus, or sorry, r squared equals 18. Square root both sides. And 18 is the square root of 9 times 2, so 3 square root 2. Now here I'll make a distinction in our notes on the next slide. When you solve for the r, the hypotenuse, it will always be positive. because like depending on which quadrant you're in, it isn't really a direction R that we know how to go on the coordinate plane. We don't go diagonally. So left, right, up, down, you use the signs like you normally would, positive or negative. But the R's we'll always assume will be positives. Can you do sine, cosine, and tangent now? Yeah. Your angle, no matter which quadrant you're in, is going to be right here around the origin. So if I were doing sine, based on what I know from geometry, wouldn't that be opposite? -3 over hypotenuse, which we called R, 3 square root 3. So -3 over 3 square root 3. Or sorry, 2. 3 square root 2. What do you notice in your fraction? You can simplify 3 over 3, so then it's just -1 over square root 2. And I heard some people also, a few people said there's a radical in the denominator. So I usually would simplify those first. And then I could rationalize my denominator. So that's negative square root 2 over 2. Okay, and then I can keep going. Cosine would be adjacent over hypotenuse. So 3 over 3 square root 2, which is 1 over square root 2, which when I rationalize will be square root 2 over 2. And then if I did tangent in the triangle, it would be -3 over 3, which is -1. Let me know if you're having trouble with my calculations or my simplifying. And then could you do the reciprocals? Yeah. Okay, cosecant, secant, and cotangent. Cotangent's really easy. What's the reciprocal of -1? Swap -3 over 3. 3 over -3. It's also -1. So the reciprocal to 1 is 1. The reciprocal to -1 is also -1. Cosecant and secant, there's a couple of different ways you could do it. Like, you could flip this final answer, but then you have to re-rationalize. So you could go back a step and you could flip this answer, 1 over square root 2, right? Then it would be square root 2 over 1, which is just square root 2, so secant is square root 2. Or you could always go back to your picture and say, like sine is opposite over hypotenuse, then this is hypotenuse over opposite. So we could do like 3 square root 2 over -3. And then, of course, the 3's cancel, and that's negative square root 2. I'm going to try to look for, like, the path that is the least amount of work for me, right? So I generally, if I rationalize once in the beginning, I will not flip that final answer because that means I'll have to rationalize again. So it means if I went into the middle of my work, there was something easier to flip. Okay, does anybody have any questions about what just happened there? I don't think you've ever done any of that in geometry. So we have to come to terms with a couple of things. It's okay to have the legs of the triangles be marked positives or negatives. Okay, but the radius will always be, the hypotenuse will always be positive. Okay. Notice that in your ratios now, this probably has never happened. Now in my ratios, some of them are positive and some of them are negative. Before, when you would do it with a triangle, all the sides were positive. So you always got positive angles or positive ratios. Now you'll have to contend with positives and negatives. Okay. When you look at those ratios, it's, negative square root 2 over 2, square root 2 over 2, 1, negative square root 2, square root 2, -1. Do those ring a bell to anybody? Those numbers? Isabella, you're saying yes? What do they make you think of?
Like the special right triangles.
Oh, they make you think of the special right triangles. So remember I gave you that half sheet, pink sheet with the special right triangles? And we did, even way back at the very beginning of this, after matrices, we did that like pink sheet with the 3 triangles on one side and 3 triangles on the back. And we found out on that first thing we did to intro the chapter that all 45, 45, 90 triangles would have the same sine, cosine, and tangent. We left it as decimals that day. But then I gave you that half sheet, pink sheet, and you labeled the sides, like the ratio of sides for the special right triangles. And if you go back and look, they're all going to be positives on that sheet because we were looking at them like geometric triangles. But depending which quadrant that 45, 45, 90 triangle is in, you're going to get those same answers. Square root 2 over 2, square root 2 over 2, 1, but they might have different signs. Okay? And you could confirm by the picture that this is a special right triangle, right? It's got a side length of 3, and even though we labeled this one -3, isn't its length 3? So it's isosceles right triangle, which means the 2 acute angles also have to be equal. Okay, so sometimes it will come out to be the same as a 45, 45, 90 or 30, 60, 90 if the ratio of sides are correct. But not always will the point I give you do that for you. Okay, so that was kind of looking at this from a strictly geometric perspective. And I'm kind of glossing over this angle in the middle for today. Tomorrow we're going to get into that angle. We're going to call it a reference angle. And so I'll be more specific about that angle. But we're going to make a definition for how to do trig functions of any angle out in space on the coordinate plane, and here it is. So you want to make sure you get this part into your notes. This is a general definition of trig functions. If you were studying trig on your own, if you were looking stuff up, online, you'd probably come across something like this in the textbook. It would be in a box. So we're going to let theta be an angle in standard position. Of course, all the angles we're really working with now, we've moved on from 9-1, they're all in standard position on the coordinate plane. And xy is a point on the terminal side. So instead of saying 3, -3, I'm just saying some x and y. So it could be in any of the quadrants. I don't know where. We're going to fill in what r is equal to here in just a little bit, but I'm going to start with a picture. So I'm going to draw my coordinate plane. It's an angle in standard position, so I know its initial side is on the positive x-axis, right? And do you agree that the terminal side could open up and land in any quadrant? 1, 2, 3, 4. Could open in any direction, could make multiple rotations, we don't know. Okay. For the sake of the definition, we're going to plop the terminal side right there in quadrant 1. That's how you'll normally see it in a definition. Okay. But it could technically be in any of the quadrants. Okay. And we have to mark a point xy on that terminal side. So before I get back into like my whole triangle piece here, when you're trying to find that hypotenuse of the triangle, you're basically trying to find this distance from the origin to the point, right? Because that's always going to be your hypotenuse. So like this side right here, this is going to be our r. And the reason why I'm calling it r now to kind of help you out with this, can you imagine that point xy being right down here on the 0 angle? And then I start moving it counterclockwise through all of the quadrants. And because that point is fixed on the terminal side, I would really be creating a circle. So like when we call it r in algebra, we're referring to it like as if it were creating a circle if it kept its rotation. So it's kind of standing for a radius. But other than the fact that that is maybe being the radius of the circle as it moves around the quadrants, we're really concerned about that triangle. So remember, when you draw the triangle, it always has to go back to the, which axis? X-axis. So in quadrants 1 and 4, you got to come back to the positive x-axis. If you're in quadrant 2 or 3, you got to go back to the negative x-axis. You always go back to the x-axis. And that's where, like you might have been noticing, like my hot colored triangles at the back wall, that's for pre-calculus. But like you're only allowed to draw triangles that look like that in quadrants 1, 2, 3, and 4. You know, whatever that angle is, those are the special angles, but it could be a 50-degree angle. I call them bow ties or butterflies. You should only be drawing me a triangle that makes a bow tie, makes a butterfly. Don't draw me a triangle that makes an hourglass. That's the one that goes back to the vertical axis. And don't try drawing any triangles from axis to axis that would make like a square or a diamond. Don't want that. I want one of those triangles. So this would be part of my bow tie, right? And you can label the sides. This, of course, is X, and this is Y. Now, if you're in quadrant 2, you can still call it X and Y, but you would know X is negative and Y is positive because you got to go left and up, right? So X and Y can have some different sign values. Well, now with this picture, and I know I'll come back and I'll fill in R here in a little bit, but with that picture, can you do your 6 trig ratios? Oops. Yeah. According to that picture, theta is going to be right here at the origin because that's where the angles open, right? As we go around in standard position, we label the angles right around the origin. What sign? Ratio of Y over R. Opposite over hypotenuse. Still a triangle. So every sign on the coordinate plane is some Y over R. And cosine is always X over R. Adjacent over hypotenuse. And tangent is always Y over X. Your angle will always be right here around the origin. So the opposite side will always be the Y. The adjacent side will always be the X. And then you can do the reciprocals, R over Y, R over X, X over Y, right? And so if you were given a point XY, you would have 2 of the values you need. You would still need R, but you guys told me to find that hypotenuse, you would use Pythagorean theorem. You can always, side note, just set up R squared equals X squared plus Y squared, right? Like that will always work. So if you like setting up Pythagorean theorem, do that. But every time you do that, R is going to solve to be the same thing. The square root of X squared plus Y squared. So that's what I'm going to put back into my definition. R is always the square root of X squared plus Y squared. When I square X and I square Y, they're both going to be positive numbers, no matter what the sign of X and Y is. So I just have to add up their squares and take the square root of that number, and that will be my hypotenuse. So, if I had a problem like this, let 8, negative 6 be a point on the terminal side of theta, evaluate the 6 trig functions. I mean, I could draw a picture, I will at the end, but I can also do it just by general definition. 8 is X and negative 6 is Y. The only other piece I would need is R. R is the square root of 8 squared plus negative 6 squared. That's the square root of 64 plus 36, which which is the square root of 100, or 10. So then the sine of theta by definition is y over r. That would be negative 6 over 10 or negative 3/5. The cosine of theta by definition is x over r. So 8 over 10 or 4/5. And the tangent of theta is y over x. So negative 6 over 8, that would be negative 3/4. Right? Okay, and then you can do the reciprocals. The reciprocals are easy here because we don't have a radical to contend with, so I'm just going to flip my final answers. Negative 5/3, 5/4, and what is it? Negative 4/3. Again, some things that you can be looking ahead that are going to be super helpful is notice that in my values, okay, x was positive, y was negative, and r was positive. R is always positive, right? So any of my ratios that involve y will end up being negative. So y over r, y over x, sine, and tangent, they're negatives because they have my negative y with a positive value. But everything, the cosine and the secant, they don't have a y in them, so they're positive. Okay, so there's a connection based on like where your point is to which trig functions will be positive and which trig functions will be negative. Okay, now I'm going to, I wanted to show just really quickly like this on a picture, and I'm not going to like redo the problem, but where is 8, negative 6? In quadrant 4. So you could say this is 8, this is negative 6. You draw a triangle back to the bow tie. And then you would have found that radius to be 10. And you could do the same thing. Opposite over hypotenuse, adjacent over hypotenuse, and you're getting the same answers. Okay, so it works no matter what quadrant you're in. Okay, will you try this one on your own? Okay, use the definition. Negative 4, 0. Find the 6 trig functions. What's r? 4. R equals the square root of x squared, that's 16, plus y squared, that's 0. So r is 4. So sine theta is y over r. 0 over 4 is 0. Cosine theta is x over r. That's negative 4 over 4, so negative 1. And the tangent of theta is y over x. That's 0 over negative 4, so that is 0. See how nice and smooth that is? What happens when you do cosecant, which is r over y, and you do 4 over 0? 4 divided by 0 is 0? Yes. You can't divide by 0. Never have, never will. So we say this is undefined. You heard that term before? For dividing by 0? You will get some if you have 0 in for x or y. You could have some trig ratios that will be undefined. Secant of theta, you can either do r over x, or you can just flip the answer to cosine, so that's -1. And then cotangent of theta, if the tangent was 0, what's the reciprocal to that? Undefined. So the reciprocal to 0 is always undefined, the reciprocal to undefined is always 0. The reciprocal to 1 is 1, the reciprocal to -1 is -1, that kind of makes things easier. Did anybody try drawing that one? Tried to make a triangle? Saw a couple people in the makings. Trouble is, what?
It's like 0, so it must be 1.
Yeah, when you try to draw that one, what was it, -4, 0? There's your point. So your initial side is on the positive x-axis, your terminal side is on the negative x-axis, and like, where exactly are you supposed to be drawing a triangle with those two? Like, you can't go back to the x-axis because you're already there, right? Or sometimes it might be like on the y-axis, and then you want to draw like this, but that would be a diamond triangle, not a bow tie triangle. So, in cases where you have these special angles, like this angle maybe is 180 degrees or pi, those are called quadrantal angles. And called quadrantal angles because they're on the quadrant, right? They're on the axes. You really have to use this definition. Like geometry, those aren't actually triangles, so you couldn't do the sines, cosines, or tangents, but we argue in algebra, if you fix it to the coordinate plane, you can by definition. Okay. So that leads me to my last topic for today, the quadrantal angles. You'll want to make sure you get this in your notes. Okay. These are the special angles because they make up the quadrants. So like think about in degrees, quadrantal angles are things like 90, 180, 270, 360, 450, 540. You can keep going around if you want, or -90. In radians, it's anything that's like a multiple of pi halves. So pi halves, pi, 3 pi halves, 2 pi, 5 pi halves, 3 pi, 7 pi halves, 4 pi. Anything that ends with pi or pi halves is going to be quadrantal. When you're asked for the trig ratios of a quadrantal, you're going to use the unit circle. And this might be your first intro to the unit circle. The reason why I have this stuff on my back wall and it's been up for a few weeks is because we're using that in pre-calculus for the unit circle. Those things that I have behind the post-its, those coordinates, they have to memorize all of those. So there's 12 plus the quadrantals, plus they have to know all the angles. They memorize the unit circle. You're going to memorize the angles probably in Algebra 2, but you won't know all the coordinates, and that's okay. But you will know the coordinates for the quadrantal angles. So I'm going to draw the unit circle, right? The unit circle has a center at 0, 0, and a radius of 1. So do you agree that those 4 points would have to be on my circle? Anytime I ask you like to do the sine, cosine, and tangent of like 90 degrees, so I'm not even giving you an ordered pair, well, you know a point that's at 90 degrees. This point, if it's on the unit circle, how many did I go left or right? 0. How many do I go up or down? From the origin? 1. So this point is 0, 1. This point is 0, -1. This point is 1, 0. And this point is -1, 0. So anytime you're asked about quadrantal angles, you might be like, well, I don't know the sine of 90. Using a circle. Use that 0, 1 as its ordered pair, x, y. Its radius is what? 1. So that's a giveaway. And then you can do y over r, x over r, etc. So let me show you an example. I'm going to make this one pi over 2. Because we just did pi essentially with the -4, 0. Find the 6 trig ratios of theta equals pi over 2. So this is different. I'm not giving you an ordered pair to like plot. But do you know where pi over 2 is? 90 degrees. Okay. So you could be thinking about, okay, that's the 90-degree angle, right? Initial side, terminal side. Here's my theta. But I can't draw a triangle with that. If you're tempted to go like this, you're drawing a diamond, not a bow tie, right? So you can't draw it. It's just like when it was over here. We can't draw the triangle. So then just pick that point. 0, 1. That's going to be x, that's going to be y, and the radius is 1. So sine of theta is y over r. That's 1 over 1 or 1. The cosine of theta is x over r. That's 0 over 1 or 0. The tangent of theta is y over x. What is 1 divided by 0? Undefined. So anytime you get those quadrantal angles, you're going to get answers like the previous example, -4, 0. That was on the quadrant, right? You're getting 1s and -1s, 0s, undefined. Like those are the type of answers you always get on the quadrants. Okay? But you can use these 4 points that would exist on the coordinate plane. Just figure out where your angle is, and then like the easiest point to pick is with a 1. And then you could of course do cosecant theta is 1, secant theta is going to be undefined, and cotangent theta is 0. Questions, concerns? Okay, your homework assignment is pretty short. I think it's 6 problems.